Hello, welcome to the NPTEL online certification course on deep learning. So, you have seen that in previous lecture we have talked about the optimization problem, particularly optimization in machine learning, and we have discussed how optimization in machine learning is different from the general optimization tasks. We have also talked about the linear and logistic regression. So, in case of linear regression, we have seen that a variable y, a dependent variable y, is predicted using a linear function of the components of the feature vector y or feature vector x, or we have written y in the form of y hat, the predicted value of y as y hat as w transpose x, where x is the feature vector and w is the weight vector. And in case of linear regression, we have said that based on this predicted value of y, you take certain decision. And we have also discussed that this linear regression at w transpose x gives you an idea of what is the distance of feature vector x from the separating plane, that is a plane having equation w transpose x equal to 0. And more the distance of the feature vector x is from the separating plane, more confident our decision is. That means, we know that the feature vector x is well within the region given to the corresponding class. In case of logistic regression, we have seen that this distance measure can be interpreted as a probabilistic measure. That means, more our confidence is that a feature vector x belonging to some class, say y, the probability of that class y given x and the parameters w, the parameter vector w should also be high. So, as the distance goes on increasing, the probability asymptotically reaches to 1. Or in the other case, as the distance goes on reducing, in the negative side, the probability of the other class goes on increasing. So, that sum of the probabilities belonging to the two classes always becomes equal to 1, because the data has to belong to either of the classes, either class omega 1 or class omega 2. So, both this linear regression and the logistic regression we have discussed with respect to the problems which are two class problems or binary classification problems. Then we have generalized this logistic regression, which is a probabilistic measure, to a class of classifiers, set of classifiers which are known as soft max classifier. So, the soft max classifier is a classifier which deals with multi-class problem. So, earlier we had seen that in case of multi-class problem, we could have a linear machine or we could have a multi-class support vector machine, where the linear machine or this multi-class support vector machine gives you class score, or it outputs a k dimensional vector, where k is the number of classes, and the linear machine or the support vector machine or multi-class support vector machine gives you a score for every class. And then for whichever class the score was maximum, we could classify the vector to that corresponding class. So, as in case of logistic regression, for a two class problem or a binary problem, that the distance measure is converted into a probabilistic measure. In case of softmax classifier, the class score can also be converted to a probabilistic measure. For that, what we have done is, given the class score plus for say class yi to be syi and class score for every class j to be sj, we have converted this class score into a probabilistic measure that p of yi given x w is equal to e to the power syi upon sum of e to the power sj, where the summation is taken over all j. That comes into the denominator, and that is what becomes a normalized probabilistic measure. And that is what you have done in case of softmax classifier. In today's lecture, we are going to discuss about the nonlinearity how considering nonlinearity is important for machine learning techniques, and then we will extend our discussion to neural networks or deep neural networks. And here it is very important, because when we talk about deep learning, the entire deep learning algorithm, entire set of deep learning algorithms are based on neural network architecture only. So, in some cases the deep learning is also known as deep neural network algorithms or deep neural network architectures. So, first let us talk about nonlinearity. So, again I am repeating the same figure that earlier we had seen, that if the classes are linearly separable, I can pass a straight line or a plane or a hyperplane in multi-dimension between the vectors given for two different classes, or in other words, that this linear function or the hyperplane can separate the feature vectors belonging to classes omega 1 and omega 2, and I can have such a hyperplane without any error. But you consider a case, say something like this: if my feature vectors are of this form. So, here all the feature vectors marked as class. So, these are the vectors belongs to one class, let us call it class omega 1, and all the vectors which are marked as minus, they are the feature vectors belonging to class omega 2. So, I have the distribution of the feature vectors belonging to classes omega 1 and classes omega 2 as shown over here. And you can well imagine, so this is the case in a 2 dimension. In 3 dimension, I can have a spherical distribution of feature vectors belonging to one class, and outside the sphere I can have feature vectors belonging to another class, and I can have many such complicated distribution of the feature vectors. So, given this, you can well imagine that here it is not possible to have a linear separator between the classes omega 1 and omega 2. Okay. Whichever straight line I form, whichever I take, I will always have some misclassification. So, this is a problem which is linearly non-separable problem. I cannot separate the classes using a linear function, or this problem cannot be solved using linear function. So, what we can do in such cases? Let me just simplify the problem. Instead of taking vectors in 2 dimension, let us consider that I will take vectors in 1 dimension, or say scalar features. So, I take a set of features. Let me draw it properly. So, as I said that I have the features in 1 dimension. So, I have a set of samples which are like this, that belongs to one class, and I can have another set of samples which I am marking in pink, which belong to a separate class. So, given this, you find that all the samples which are marked in pink are sandwiched between the samples which are marked in blue. So, given such a case, I cannot draw a straight line, or I cannot separate the samples belonging to these 2 classes using a single point on, say, line x. So, this is the feature direction. I cannot have a single point on this feature line x which separates the samples belonging to class omega 1 and the samples belonging to class omega 2. I can of course separate them if I take a curve of this form. Okay. Or in other words, I have got 2 points on this feature line using which I can separate these 2 classes. So, this becomes a nonlinear problem, it is not a linear problem anymore. So, how to solve this? I can still solve this by having some nonlinear mapping of the feature vectors, right. So, what I will do is I will have a nonlinear mapping of these feature vectors in such a way that these feature vectors will be remapped in this direction. Okay. So, as a result, the feature vectors, all the feature vectors belonging to class say omega 1, let me redraw this figure. So, all the feature vectors which are marked in pink, they will be mapped over here, and all the feature vectors which were marked in blue, they will be mapped over here. So, you find that I had features in one dimension, now they are mapped in 2 dimension. So, the first thing that I am doing is I am increasing the dimension of the feature vectors. And how I am doing it? I am doing it by using a nonlinear mapping. I will come to what form of nonlinear mapping we can do. So, I am doing it using nonlinear mapping. And once I have this, now you find that I can pass a straight line over here which separates the feature vectors which are pink from the feature vectors which are blue. So, one way we can tackle the problem of nonlinearity, that is if the feature vectors are mixed. So, that problem can still be solved using a linear classifier, but for that instead of trying to use a nonlinear classifier, you apply some nonlinear mapping on the feature vectors, and once the feature vectors are nonlinearly mapped, possibly on a higher dimensional space, in that higher dimensional space the feature vectors can be classified using a linear classifier. So, what we will do in that 2-dimensional example that we have just shown. Let us go to this 2-dimensional example again. So, the example was like this. Okay. So, what I can do here is you find that this is something like a circle at the center, and the feature vectors belonging to class omega 1 are within this circle, and all the feature vectors belonging to class omega 2, they are outside the circle. So, I can have a nonlinear mapping of these feature vectors, say nonlinear mapping using a nonlinear function say phi. How this nonlinear function will work? You find that I have feature vectors in 2-dimensional space which is given by x 1 and x 2. If I introduce a third dimension, say I want to have a value of z, where z will be equal to x 1 square plus x 2 square, right. So, if I do that, then you find that for any feature vector which is outside the circle, so over here the value of x 1 square plus x 2 square will be more than the value of x 1 square plus x 2 square for any feature vector which is within the circle. Because for any point on the circle, x square plus x 1 square plus x 2 square is nothing but square of the radius of the circle. And because all these feature vectors which are negative are outside the circle, for them the square of the distance will obviously higher than the square of the radius of the circle. So, for all these feature vectors which are outside the circle, x 1 square plus x 2 square or the value of z will be more than the value of x square plus y square for any feature vector which is within the circle. So, what I will do is I will now represent all these feature vectors. So, in the original form the feature vectors are 2-dimensional having components x 1 and x 2. Now, I will add a third component z which is x 1 square plus x 2 square. Okay. So, now my feature vectors will be x 1, x 2 and x 1 square plus x2 square. So, this becomes my feature vector. So, you find that I have applied a nonlinear function which nonlinearly maps these feature vectors from a two-dimensional space to a three-dimensional space. And when you consider in the third dimension, that is in the dimension of z, for all these feature vectors which are within the circle having mark positive, for them the z value is less than the z value of the feature vectors which are marked negative. That means, when I consider in the z dimension, all the feature vectors which are negative is somewhere over here, and all the feature vectors which are positive is somewhere over here. So, once I have this, then I can always pass a plane in between which is passing through the feature vectors belonging to one class and the feature vectors belonging to another class. So, by this nonlinear mapping on the feature vectors, I am converting a linearly non-separable set of feature vectors to a linearly separable set of feature vectors. And we can say that this is being done by a nonlinear mapping phi, and this phi is nothing but a collection of three functions phi 1, phi 2 and phi 3, where phi 1 and phi 2, phi 1 works on x1, x2. So, I will write it in this way. Let me clear this. So, x is my feature vector which is having two components x1 and x2. So, phi of x, I can write it as phi 1x, phi 2x and phi 3x. What is phi 1x? Phi 1x gives you x1, phi 2x gives you x2 and phi 3x gives you x1 square plus x2 square. And that is what is the nonlinear mapping that we are going to have. So, you find that now I have converted these feature vectors from x1, x2 plane from 2 dimension to 3 dimension, where now the dimensions are given by phi 1, phi 2 and phi 3. So, I can simply write this as the space. Now, I can represent as I am having 3 dimensions. I can put it like this is phi 1, this is phi 2 and this is phi 3. And once I have this, you find that the hyperplane in this phi 1, phi 2, phi 3 space can now be written as, say, W1 phi 1 plus W2 phi 2 plus W3 phi 3, that equal to 0, right. And now, if you expand this phi 1, phi 2 and phi 3, what I have? Phi 1 is nothing but x1. So, this simply gives you W1 x1. Phi 2 is nothing but Wx2. So, that gives you W2 x2 plus phi 3 is x1 square plus x2 square. So, I have W3 x1 square plus x2 square, which is equal to 0. That is the equation of the plane that I have. Now, I find that I can have a dual interpretation of this equation, in the sense, if I consider this equation where my variables are x1 and x2, the equation is a nonlinear equation, right. Whereas, while training, I am given the training vectors. That means, for all those training vectors x1, x2 are fixed. So, I can also consider this equation to be an equation in W1, W2 and W3, where W1, W2 and W3 are the variables. But because the feature vectors given for training are fixed, So I can also consider x1 and x2 to be constants. So if I consider x1 and x2 to be constants, then this equation is a linear equation. So if I consider this equation to be an equation in x1, x2, it's a nonlinear equation, which gives you a nonlinear mapping of the feature vectors. So the feature vector x1, x2 is nonlinearly mapped into phi 1, phi 2, phi 3 domain. And the classifier or the separating plane is a plane where w1, w2, w3 are variables and x1 and x2 are fixed. Okay. So by this nonlinear mapping, you are mapping the feature vectors into another space and possibly a higher dimensional space, and in that higher dimensional space, the feature vectors are linearly separable. So we'll come to, so this is a very simple example where using a simple mapping, I can convert a linearly non-separable set of feature vectors into a linearly separable set of feature vectors. However, the type of nonlinearity may not be so simple. There can be complicated nonlinearities, and those are the nonlinearities which are to be solved by the neural networks that we'll see later, and the neural networks are to be trained using the training vectors. So I'll come to those problems later. Okay. So what are the different types of, so it is quite clear that when I have a linearly non-separable problem, I have to have nonlinear mapping of the feature vectors from one space to another space. And in most of the cases, this mapped space is of higher dimension than the original space. And theoretically, it can be proven that if I map feature vectors to infinite dimensional space, then whatever be the complexity of the nonlinearity, every nonlinear problem can be solved as a linear problem when you are increasing the dimension to 0. And for such nonlinear mapping, I have to have some nonlinear functions. So now let us see that what are the different kinds of nonlinear functions that can help us in such a nonlinear mapping. So one of the nonlinear function which we will use is what is known as threshold function. It is a very, very simple function. So the threshold function says that if y is a function of x, then output y, the dependent variable y, will have a value of 1 if x is greater than or equal to 0, and it will have a value of 0 if x is less than 0. So here this nonlinear function is depicted in this form. So as x is greater than 0, value of y is 1. So here it is 1. If x is less than 0, the value of y is 0. So here it is 0. So this is the simplest kind of nonlinearity, which is a threshold function that we can have. And we'll see the use of this sort of nonlinearity when we start our discussion on neural network. The next type of nonlinearity, which we have already discussed, is logistic regression. You find that this mapping that we have done from W transpose X to sigma W transpose X is nothing but a nonlinear function. Okay? So this sigma W transpose X, which is 1 over 1 plus e to the power minus W transpose X, this is a nonlinear function. So this function also helps us to transform a nonlinear problem to a linear problem. The other kind of nonlinearity, which is widely used in case of neural network or modern deep neural network, is what is known as ReLU or rectified linear unit. So this rectified linear unit simply puts as, if y is a function of x, then y will get a value of maximum of 0 or x. So naturally you find that if x is greater than 0, y gets the value of x, and if x is 0 or less, y will have a value of 0. So for all positive x, y and x are same, For 0 and less, if value of x is 0 or negative, then y will assume a value of 0. So, I can depict this function in this form. So, here you find that as x is greater than 0, y is equal to x. So, if you take the gradient of this slope of this line, this slope is nothing but 45 degree. So, as y is greater than 0, value as x is greater than 0, y becomes equal to x. If x is less than 0 or 0, then value of y is 0. So, this is a linear rectified unit, a rectified linear unit, which is in short it is written as ReLU. And obviously, you find that it is also a nonlinear mapping. This also gives a nonlinear mapping, because if y is equal to x or y is some constant a times x, that is a linear function. But the moment I put y in this form, it is a nonlinear function. So, in case of neural networks, we will see later that in simpler cases, we can use threshold functions. In most of the popular neural networks, the nonlinearity that is used is a sigmoidal function. But in modern neural networks, in deep neural networks, instead of sigmoidal function, people prefer nonlinearity. The reason is threshold function is a simple sort of nonlinearity. For simple networks, we can use that. But the problem with the threshold function is it is non-differentiable. I cannot differentiate the threshold function. And we have seen in training earlier that in most of the cases, training uses a gradient descent approach, where gradient is nothing but a differentiation, right? Differentiation in multiple directions. So, because threshold function is cannot be differentiated, it is a non-differentiable function. So, there it leads to problem in case of training of the neural network, because gradient descent cannot be applied on that. So, that problem is slightly overcome if we use sigmoidal function as a nonlinearity. Of course, sigmoidal function is not the only one. The other kind of nonlinearity which people also have tried is what is known as tan hyperbolic nonlinearity, where you have variation of the output from -1 to +1. In case of sigmoidal function, it is 0 to +1. So, tan hyperbolic kind of nonlinearity has also been used, but there again the problem is when the value of W transpose X is very high, or the value of the argument is very high, the gradient is very, very slow, right? Because your curve is almost parallel. So, gradient almost vanishes. And because of that, your training or the learning algorithms becomes very slow, which is solved by this ReLU. Because in case of ReLU, as long as x is greater than 0, the gradient of the function is unity, right? So, here the gradient does not vanish. So, that is an advantage of ReLU. And when you have modern deep neural networks where you have large number of nodes, large number of layers, hidden layers, then ReLU becomes more advantageous over sigmoidal function. So, today we have discussed about nonlinearity, and we will continue with these discussions in our next lectures. Thank you.